Uh, Hello, this is the seventh lecture of 11123. And we will be talking about bipolar junction transistors and how they behave when we connect them in circuits. How do we analyze BJT circuits? So, just a note to everyone listening here, uh, Module 7 is BJTs in circuits. We won't dive deep into the physics of how BJTs operate. Okay? So, the coverage of this lecture, I will introduce to you the how a BJT operates, right? And how do we or how a BJT basically is made, right? So in terms of semiconductors, how can we build a BJT? How does it operate in a circuit? What are the models that we can use to simplify our analysis with BJT circuits and examples of BJT circuits? Right. So let's start with some history and our very first the first few or the one of the first computers, electronic computers rather, that was built in 1946 is the ENIAC, as you see here. So the ENIAC uh, uses a large area. As you can see, it uses 167 square meters of area just so it can operate. It uses 150 kilowatts and its processing frequency is 100 kilohertz. Right, fast forward to 2012, a, a small chip such as the i7, which uses 160 square millimeters of area, basically fits on the palm of your hand, uses 50 watts of power, has more processing capabilities compared to ENIAC. And this is how far we have come. So the development of the Intel Core i7 can be attributed to the rise of transistor circuits. And BJT, or bipolar junction transistors, are the first to be designed and conceptualized. Right? So the semiconductor family tree, quote unquote, is what you see here. We've already talked about diodes from Module 6, right? But we did not dig deeper into it, just some basic diode models, right? Just two of them, ideal diode model and the one with the voltage drop. Right? And the diode actually has three types: the rectifier, Schottky diode, and the Zener diode. Right? Transistor has two types. So the transistor has a bipolar junction transistor, and the other type is the field effect transistor. That's what you see here. Right? And there are also some others aside from diode and transistors that are used extensively in our modern electronics, but we won't talk about that here in this course. So we only consider the transistor for this, specifically the bipolar junction transistor. And transistors have two main functions. Right? First is amplification. So signal amplification, normally our audio signal, sensor signals, all of that. Very small amplitude, right? Very small, very weak signals. We need to be able to amplify them so that we can harness or we can measure our signals, basically. Another use of the transistor is switching. So switching is the basic function of a computer. By enabling switching, we're able to calculate or perform complex mathematical operations using our electronics. Right? And the transistors are used for all of that. Right? So let's talk about transistors. Transistors is short for a transfer resistor. Why is it named that way? It's because if you have an input, right, the resistance at the output changes depending on your input. So you're transferring this uh, output, sorry, transferring this input to another output at a different part of the circuit. They could be disconnected from each other. Right? That's why it says transfer resistor. And there are two types. Two types is the bipolar junction transistor. Wait, I apologize. Right, there you go. One type is the BJT or the bipolar transistors. There are two types under that, depending on how it is structured and made. The other type is the field effect transistor. Right? Under the field effect transistors, there are also two types: the junction FETs and the MOSFETs. And for this course, we won't talk about JFETs. Right? A more useful field effect transistor, in my opinion, are the MOSFETs. And MOSFETs are uh, used more in electronic circuits. And sorry, in computer circuits, computer processing systems. BJTs are used more in amplification. Okay, so let's focus on one type of BJT, the NPN BJT. So the bipolar junction transistor has three terminals: the emitter, base, and the collector, as you can see in this figure here. So the emitter, for an NPN transistor, the emitter and the collector are both N-type semiconductors. And the base is a P-type, an opposite sandwich between your emitter and your collector. Okay. The emitter, by the name, emits or injects free electrons to the base. In this way, okay, these free electrons, when injected to the base, will be collected by the collector. And to do that, for the emitter to be able to emit free electrons, the base must be activated first. Right? So the base must pass all these carriers from the emitter to the collector. So by activating the base first, right, by injecting a current in the base, carriers are free to flow from your emitter to your collector. Therefore, uh, therefore, you have some form of current between your emitter and your collector. So you control this current depending on how you inject electrons or how you inject energy in the base. Okay, so the NPN BJT has or can be drawn in a schematic shown here. It has three terminals, right? And the collector is normally at the top. The emitter has an arrow, okay, going out, and the base is connected to a line right here representing uh, control over the junction. Okay, the arrow always points away from the base toward the emitter for an NPN BJT. Okay, so this is your schematic or a symbol for your BJT. Right. So there are 6 quantities that are of interest when we are analyzing an NPN BJT. So 3 voltages and 3 currents. We have the base current being injected to the base, a collector current that flows from the collector to the emitter, and your emitter current that flows out from your transistor. But since the emitter emits free electrons, shouldn't the current flow from the emitter to the collector? The actual current flow is from the emitter to the collector, but we're talking about electrons. So since we're talking about electrons, then the conventional flow of current, using the conventional definition of current, is actually from the collector towards the emitter. Okay, now going back to the structure of your bipolar junction transistor, it looks like two diodes that are connected side by side. Since a diode is a p-n junction, recall from the previous lecture, it looks like this NPN BJT is two diodes back to back. Okay? So if we have two diodes that are back to back with each other when we're analyzing diode circuits, how many possible states do we have? So since the diodes can just either be on or off, then your transistor has 4 states. When both are on, when one is on and the other is off, and when both are off, consisting of 4 different possible states for your NPN BJT. and that is defined here. The regions of operation of a bipolar junction transistor is shown here. Okay, so it all depends on VBE, which is the voltage drop between the base and the emitter. It also depends on VBC, which is the voltage drop from the base to the collector. Okay, so the voltage drop between them, right, is defined by the potential difference, basically. And if both are on, right, if both of them are on, current flows everywhere. Current will flow everywhere. This will saturate your transistor with a large amount of current, okay? And you are in the saturation region. There's a lot of carriers, there's a lot of current. Your transistor cannot keep up with the amount you are injecting into the base. That's why it's saturated. When both are off, there's no current flow. So you are in the cutoff region of your transistor. Okay? And the other two is uh, when VBC is turned off and VBE is turned on, you are in the forward active region. And this is the best region to use when you want amplification. Right? Reverse active region is the opposite of that. But we don't really use it that much. It's not efficient. Right? Forward active is used more for amplification. These two states here, cutoff and saturation, are used for switching, basically. If you want to, if you want current to not flow, you cut it off. If you want current to flow, you saturate your BJT. Okay, and this is the characteristic curve of your bipolar junction transistor. Okay, so you have a resulting collector current depending on VBE, and VBE also controls the value of VCE. So let's look at this. If you are in the forward active region, you are in this region. And in this region, for any value of VCE, as you can see here, your IC, your collector current, is maintained constant. Okay? The collector current is maintained constant over a large value or a large range of values for VCE, which makes the behavior of your bipolar junction transistor synonymous to that of a current source. In the forward active region, the transistor acts as a current source that is dependent on the value of VBE. If you increase your VBE, IC will also increase. Right? And this is how the energy or the property of your BJT uh, is dependent on the input. Right? So it's not a current source per se, it's actually a dependent current source. So the dependency of this current source is on IB or VBE. Right? And in this region right here is the saturation region where IC fluctuates. Let me just change the color. Where IC fluctuates in different values. Okay. This is also saturation region. IC fluctuates. Reverse active region is the same as the forward active region. Okay. So you have a constant IC for a large range of values of VCE, and at very small values of VBE, right, where IB is approximately 0, your device does not let any current flow through it, and that's how a bipolar junction transistor works. Okay? Another parameter of interest is relating the current IC to the input VBE. So the relationship between them is defined by this function, where VA is called the early voltage. Okay, so VA is called the early voltage. IS is the saturation current. Okay, the reverse saturation current. VT is the thermal voltage. Okay. VCE is the voltage across your collector and emitter, and VBE is the input voltage at the base emitter junction. Okay. And take note, this is just a model of the relationship between IC and VBE, an accurate model, I can say, but it's not always accurate for large values of VBE, as you can see here. For a 2N2222A bipolar junction transistor, it kind of deviates largely in the higher values of VBE. But in the smaller values, we have a small error, right? And we can use it. We can still fairly get an accurate analysis, even if we use this model for your IC versus VBE curve. Okay, so this is widely used. And IC, if VBE is large enough, IC is equal to this expression, this small expression. And it looks like the diode expression, Shockley's equation. Okay. But instead of VBE versus IB, the VBE defines the current IC that is flowing on the other side, at the output side of your BJT. Okay, there you go. And that's how a BJT circuit operates, or a BJT device. Right. So how does amplification happen in BJT? I mentioned before that BJTs are widely used for amplification. Okay. So how does it work? Well, consider a small part of your a small part or a small change in VBE right here, a small change, and that change, project that to your IC. Take note of the scale of IC here. It's by the 50 milliamperes. A small change in VBE, that is around 10 millivolts of change, right? Just 10 millivolts, very small change. There's already a fluctuation of 8.8 to 9 milliamperes, a variation of IC. So imagine this as a signal. Let's say it's a sinusoid, a very small sinusoid, 10 millivolts of amplitude. This IC will vary wildly from, if you have a 10 millivolt amplitude sinusoid, this will vary from negative 9 milliamperes to 9 milliamperes. Okay, uh, from your mean IC. Okay, from your mean. So there's a large amount of change in IC because of just a small change in VBE. So imagine if you have a resistor here. Right? If you have a resistor here connected to a voltage source, right? If you change IC, right, by 9 milliamperes, if this resistor is just 100 ohms, then you have a 0.9 volt change in voltage, right? At a 0.9 volt change in voltage here at this 100 ohm resistor, just because of a 10 millivolt change in VBE. So imagine using VBE as the input port for a very weak signal. 10 millivolts is very weak. Right? And IC will amplify that. Right? This is still the same signal that is being still the same signal. This is the output at the other side of the circuit. But you have a 0.9 volt change in your voltage. So from 10 millivolts, you now have a 0.9 volt fluctuation. Right? And that corresponds to this region in your BJT output characteristic. So for a 10 millivolt change, your output can change from around 0.8 volts to 4.5 volts. So that amount of fluctuation can be noticed even by a very small fluctuation at the input of VB. And that's how amplification works for BJTs. Okay, so now let's move on to how we model the BJT in circuits. First model is the cutoff model, when there is a small current, right, just approximately zero, very small. There's no current flowing. I apologize for that. Just uh, I'll just, oh wait, I still have some time for this one. Alright, so a very small IB, okay? If IB is very small, then there will be no current flow across your BJT. Okay. The forward active region has a model like this, where your BJT will act as a dependent current source that will depend on the value of IB. Okay? So they will be related by a ratio of beta, where beta is called the current gain factor. So beta is the current gain factor, and you also have a diode that is in forward bias when your BJT is in the forward active model. Okay, or your BJT is in the forward active region rather. So normally this is just modeled as a constant voltage drop at 0.7 volts. Okay, and beta is always given. If it's not given, it depends on the type of BJT you use. So for 2N4 or 2N3906, I think if I remember correctly, beta is between 50 to 150. Okay? For a 2N4401, I believe if I remember correctly, beta is from 150 to 250. Okay? The higher the beta, the better the amplification. Okay? Another model looks like this. You'll still get the same analysis, same answers if you use this model, the pi model. Right? Again, your IC is dependent on IB. So IB is kind of transferred towards IC in the forward active region. Finally, a BJT model in saturation mode, basically you just have two diodes, right, that are facing each other back to back. Both of them are in forward active mode. Basically, you have a VBE here, a constant VBE, and you have a constant VBC on the other side, having VCE, a constant VCE right here. We call it the VCE saturation, which is normally around 0.2 volts for a lot of BJTs. So your VCE is fixed at that value, and IB, or IC rather, is no longer equal to beta times IB. In reality, actually, IC is less than beta IB. If IC is less than beta IB, you know you are in the saturation region of your BJT. So now, if we put it in a circuit, how do we analyze a BJT? So since it has three different models, how do we know which is which, right? For diodes, we assume a state. And if there's a contradiction in our calculations, then that state that we assumed is wrong. The same principle can be applied to BJTs. So the basic steps are outlined here. The first step is to assume that the transistor is forward active. Right? It's systematically that way. The best bet is the transistor is forward active. And if that is true, then IC is strictly equal to beta IB, and VB is equal to VBE on. And you solve for IB first. So solving for IB, if IB is less than 0, then the transistor is actually in cutoff. And you redo the calculations with IB, IC, and IE equal to 0. If IB is greater than 0, you solve for VCE. So you've already solved for IB, you can solve for IC easily. Then you solve for VCE. If VCE is greater than VCE saturation, which is normally 0.2 volts, your transistor is in the forward active region. If VCE is less than the saturation voltage, then the transistor is saturated. With that, since the transistor is saturated, then you must redo all the calculations by setting VCE to a constant value at VCE sat and setting VBE also in a constant value, VBE on. And then you redo everything. Okay? So you always start with the forward active assumption. Right? Always start with the forward active assumption, and that's the best bet that you have. So unlike diode circuits where you randomly assume a state, for BJTs you always assume forward active first and then find the contradictions. Right. So that's the end of the first part of the lecture. If you have any questions or comments, do not hesitate to leave them in the comment section below. Thank you for listening. See you next meeting.